Hi everybody, welcome back. This is Adam Clark and we're hanging out in the Hazardous Weather Testbed. Last time we were talking about a potential severe weather event on May 16th, and the forecasts that we were looking at were 3 days beforehand. The website that I'm displaying here shows the storm reports that occurred on May 16th, and this was quite a big day for severe weather. So unfortunately, there was a tornado outbreak and there were several strong to violent tornadoes that occurred. There were 3 EF3 tornadoes, 2 EF4 tornadoes, and several other weaker tornadoes, and just a really widespread swath of damaging wind and hail reports. So if we look at some of the more specific reports that occurred, here unfortunately in the St. Louis area there were 5 fatalities with an EF3 tornado. In Missouri, near Stoddard, there were 2 fatalities. And then in Kentucky, there was a EF4 tornado with a particularly long track that was associated with 19 fatalities. So this was really a significant event. And we're going to take a look at some of the model forecasts that we showed last time and see how well they were able to predict the event. So the first thing I wanted to show, one of the things that we evaluate is these forecasts from single models. We call these deterministic predictions. And each day in the HWT, we will look back at previous days and we'll assign subjective ratings to a set of deterministic models. So the particular comparison here is looking at a model called the RRFS, and this is in the panel in the bottom middle right here where my cursor is. And the other models being displayed, the National Weather Service plans to retire them, and then the RRFS will replace those models. So the goal of this comparison is to see whether the RRFS is able to perform as well as or better than these models so that the Weather Service can safely retire them. And so we're just going to show what the predictions looked like for this event. And so these panels are showing forecasts of what the future radar will look like. The observations are on the lower right, and right now I have the previous evening, and then as I animate this, we go into the morning of May 16th. And so I'm going to focus on the observations first in the bottom right. And this was an unusual event because it started really early in the morning with severe storms that formed along the Ohio and the Mississippi River. And these were mainly associated with hail and wind reports. And so you'll see those progress to the east. And notice that each of the models here have different depictions of that event. But importantly, they did generate storms that were quite intense at about the same time and location as we saw in the observations. So as we go later into the morning and into the afternoon, those storms progress eastward through eastern Kentucky and West Virginia, and this was really the main show. So you see these, what we call discrete storms. These could also be referred to as supercells because they have sustained rotating updrafts. And then you'll see the storm right here where my cursor is pointing to. That's the St. Louis metro area. And there were, if I overlay the tornado reports, you can see by these red triangles that there was an EF3 tornado that went through St. Louis. So the models, again, have various depictions of the event. There are good things and bad things that you can point out. So for example, the RRFS is able to get the initiation, but it's a little bit late. So notice that when these storms formed in south central Missouri, the storms hadn't formed yet in the model, but just an hour later they had. And they did have the storms going through the St. Louis metro area. So as we go later on, you'll see this storm right here in Kentucky produced a long track EF4 tornado. And a good thing about the RFS is that it did have discrete storms in that area. It didn't have the forecast exactly right. And also notice this large storm in southeastern Kentucky does not match with where there was an observed storm in the radar reflectivity here. So this is just an example of what we do in the HWT when we're conducting these model evaluations. We look and interrogate the forecast really closely. We look for things like the timing of convective initiation, where there are hits, where there are misses, where there are biases in the intensity of storms. And so in the end, we end up compiling all of these subjective ratings that all of our participants assign to the model forecast. And then we can say and make plots of how well the models performed. And so that's what I'm going to show. Now, our experiment isn't over yet, but we compile these ratings each week so that we can track how the different models are performing. One important aspect of these evaluations is that when the participants do them, they're blinded. So you can't see which model is which. And so if somebody has a favorite model or they're from a particular agency that generated that model forecast, they don't have any personal biases for or against the models that we're rating. And so what I'm showing here, these are violin plots. They're kind of like fancy box plots, and they're showing the distributions of the subjective ratings on a scale of 1 to 10. And 10 is the highest number on the y-axis, 1 is the lowest number. And so you want to see the fattest parts of these distributions be higher up on this scale. So the labels here at the bottom, the models are ordered from the ones that performed best to the ones that performed the worst. Throughout the entire experiment, the RRFS model in this evaluation has performed the best. And so this is a really good thing because the RRFS is scheduled to replace all of the other models that we're evaluating. And so the plot on the left is showing the evaluation results for the simulated reflectivity, or what the future radar looks like. And then on the right, it's showing the ratings for how well the environment feels. So temperature, dew point, instability, how well they were depicted. And for both of them, the RRFS is coming out on top in these evaluations. So the next thing that I wanted to show is following up on some forecasts that we displayed in the previous video. And these forecasts are from a machine learning algorithm that was developed at the National Center for Atmospheric Research in Boulder, Colorado. The plot on the upper left is showing severe weather probabilities from a neural network algorithm. And these use data from a coarse global ensemble. And then in the upper right, it's a similar machine learning algorithm, but it uses data from a finer resolution convection allowing ensemble. So it contains information that is very specific, that comes from both the forecasted storm attributes and aspects of the forecasted environment. So if we overlay the storm reports on these probabilistic forecasts, we can get a sense for how well they did. So let's do that. The upper left, you can see these 60% probabilities in the dark purple correspond very well with where the most impactful severe weather occurred. And then when we look at the areas farther east across the mid-Atlantic, you can see that there's an extension of higher probabilities that corresponds pretty well with where we had clusters of severe wind and hail reports. The upper right, you can see that the location of that 60% probability is pretty good, but look to the north. So these areas of northern Indiana, Ohio, and then as we get into the Washington, D.C. area, don't have as high of severe weather probabilities like the algorithm on the upper left had. So these forecasts would have likely been rated a little bit lower. And this is a somewhat counterintuitive result because we sometimes expect to get better information when we're running these convection allowing ensembles. but they can also introduce errors. And in this particular case, the convection allowing data did not add value to the machine learning algorithm. And so during the experiment, we'll look at these types of cases over many, many days and then compile the aggregate results similar to what I showed in that previous plot. Thank you for watching. If you have questions, leave them in the comments and continue to stay weather aware.